Okay. Hi, everybody. Thank you for being here. At lunchtime also, we appreciate it. Today, we are talking about quantum computing, which is, I think, one of the most interesting topics of the last few years. This is not really the same as AI or Gen AI, which is the main theme of this conference, but considering the significant improvements in the AI technology, maybe we could see the same improvements in the quantum computing technology. And so it's time also for us as software developers and engineers to start studying quantum computing and experimenting with its principles. So my name is Matteo. I work as a software engineer. I'm not a physicist. And my goal for today and for you is to show you that you don't need quantum computing, you don't need PhD to try quantum computing. Okay, so a few words about me. I'm a software engineer, as I said. I work at a company called Kinetics. We mainly do operating systems and fleet management for embedded systems. I'm more involved in the application software, so I write embedded applications and also cloud and serverless applications, mainly in Scala. So I'm a Scala developer, and I've been so for 5 or 6 years, more or less. An important thing here is that I don't have any quantum physics or quantum mechanics background. So I want to show you today that you don't need it either, and to also to share my journey in learning the principles behind quantum computing and learning how to leverage them even without a deep mathematical knowledge. We'll be doing so by first looking at what quantum computing is very quickly. We will not go into the equations or into any deep theory, and also why we believe it is useful and it will be useful in the future. Then we'll move to seeing how classical software developers and engineers like us can do about quantum computing. What can we do about it? What can we do to learn it? In particular, with attention to the quantum computing simulation. So today we have many technologies and libraries to simulate on a classical computer that we use every day the principles and the computation that's normally done on a quantum computer on a quantum physical level. And then we'll conclude with a few observations about what we saw today and also the future of the field. So first of all, does any of you know something about quantum computing? Have you heard about it? Okay, so quite a few people. And what's the first thing that you think when you think about quantum computing? What's the first purpose in your minds? Anyone? Encryption? Encryption, of course, yes. So encryption is the main thing. Like most of the hype is about making encryption less secure or more secure, depending the way you're standing at it. There are also more things about quantum computing, and actually, in the beginning, the main idea, the main drive behind quantum computing was simulation. Now, in the 1980s, Richard Feynman noticed that there are some quantum experiments, so things happening at a quantum particle level, that are not easy to simulate using a classical computer. Now, the reason for that is that quantum experiments are probabilistic, but then Feynman said, well, maybe also these quantum experiments are capable of doing computation that a classical computer cannot. And it turns out he was right, because there are many problems that are not easy to solve on a classical computer. Encryption is full of those that are kind of much easier on a quantum computer. And the important thing here is that this is not about increasing just the computational power of classical computers, because we've been doing so almost exponentially since the 1980s. It's all about changing fundamentally how the computation itself is done. And I'll be back on this in a minute. But first, I wanted to say that quantum computer will not be useful for everything. It is not a technology that we can use on any possible problems, and many areas are still unclear if quantum computing will be applicable to them or not. Cryptography, we know almost for sure. Also simulation, chemistry, quantum chemistry, physics simulation, also material simulation, drug simulation. We have promising results with quantum computers, but there are many other things that will be faster on a classical computer. So in the future, we are almost sure that quantum computers and classical computers will coexist. So we'll have classical applications written in Java, for example, invoking quantum algorithms and using their results almost as we normally use third-party services to get some results during our computation and our programs. So the role of classical software engineers and developers will be very important also in the quantum computing era, if there will be such an era, because of course classical applications will have to be written by some people. Okay, so I said before that the reason why quantum computing is so fundamentally different is that there is an entirely different type of computation. Now, this is the only theoretical slide that I have, so don't worry, it gets better than this. Just to explain the difference between the bit, which is the fundamental unit of information in classical computers, and the qubit, which is the same thing but in quantum computers. Now, as I'm sure you know, a bit is a discrete entity. It can be either 0 or 1, with no other possible values. The same is kind of true for qubits as well. We have two basis states, this 0 and 1 that you see there in the formula. But qubits can also be in a superposition state. Now, some people say that this means that the qubit is at the same time 0 and 1. Which you can almost see from here, from this part of the equation, which is not really clear to me because a qubit is also at the same time neither 0 nor 1. A better explanation, I think, is to say that when the qubit is in superposition, we don't know its state. We only know the probability for reading 0 when we read the qubit, when we measure it, or the probability for reading 1. And the probabilities are linked with these two quantities here, alpha and beta, that you see in the equation. So this is important. We don't know what the value of the qubit until we measure it at the end of the computation. This is the real difference. Now, qubits are generated by a quantum phenomenon. And the research world is full of examples today. A lot of effort is being put on finding different approaches to generating qubits that are stable enough and for the real amount of time that we need to use them for something meaningful. We have different possibilities. Different companies such as Google, IBM, or Microsoft, they're using all different approaches to the qubit generation. So we have many possibilities, and there is no real winner. Today, we'll still have to figure out many things. The most important thing is about the noise. So a qubit is a physical particle and is subject of interference from the external world. For example, room temperature might affect how qubits are measured or their value, electromagnetic interference as well, miscalibration of the computers, another thing. Also interference from different qubits. If we have many qubits in a single system, they can interfere with one another, which is something that we don't have on classical computers. Okay, so this is also an important problem, the noise today. I'm sure this is all very theoretical, so let me give you an example to bring it a little bit into the macroscopical world. So the example I'm going to give you today is about the Schrödinger's cat. Probably you've heard about it. This is actually a paradox in quantum mechanics to show how weird and absurd quantum principles appear when we apply them to the macroscopical world. So in this paradox, we have a cat, which is alive at the start of the experiment. We put the cat into a box, and then we close the box. The box is sealed. We cannot see its state from the outside. But in the box, there's also a bottle of poison, let's say, which has 50% chance of breaking and releasing the poison, or 50% chance of not breaking, leaving the poison in the bottle and not killing the cat. This 50% chance is given by some kind of quantum experiment. We're not interested in what the experiment actually is. But still, you have to know that there is a true, real 50% chance for the cat to die when this experiment goes off, and 50% chance for the cat to remain alive. Now, imagine our qubit is the cat. The first important thing about the experiment is that when we initialize a qubit, we know its state. We know that at first, the cat is alive. So we can say state 1, for example. Okay? Then we put the cat inside the box, we close the box, and we trigger this quantum experiment. And then at that moment, we don't know the state of the cat anymore. The cat is surely not at the same time dead or alive, but we don't know if the cat is dead, because we have 50% chance of the poison to be released, or if the cat is alive, because we have 50% chance of the poison not being released. Okay, so this is superposition. We don't know the state of the qubit, we only know the probability to find the qubit in a given state, either 0 or 1. And it turns out that the whole quantum computing thing is about manipulating these probabilities. We can manipulate probabilities to make wrong solutions not likely to be measured, to be read, and correct solution more likely to be measured and to be read. Then when we open the box, we are making what's called, in quantum mechanics, a measurement. And quantum systems, they have this property that they are so small that whenever we measure a quantum system, we're actually destroying its state. When we open the box, the cat is either dead or alive. So we basically reduce a qubit into a classical bit by observing it, by measuring it. And this is very important, and we say that measurement destroys superposition. So this is it. This is how a qubit behaves. Of course, it's much more complex on a quantum level, but the basics is this one. And what about the noise? Well, the noise could be, for example, the room temperature makes it easier or more likely for the bottle of poison to be broken, right? So for example, if you have more than 30 degrees, then we have 80% chance for the poison to be released. This is noise. It affects the measurement and also the stability of the qubit in the long run. Now, this sounds very theoretical, and at this point, you might be wondering what's in it for software developers. Why should we even care about it? Surely, it's very difficult that we have to write quantum algorithms. At the moment, this is just something for physicists or mathematics people and mathematicians. And also, large-scale quantum computers, for example, those capable of breaking cryptography or to factor large numbers, are still many years away. They say 20 years, 15 years, like the estimates depends, but still, these large-scale quantum computers are still many, many years away. And so why should we even care right now about quantum computing? Well, the first thing is that it's fun. It's just very, very nice to experiment with quantum computers and to understand the principles that are behind this new type of computation. Plus, in the future, we might have to be exposed to quantum computers at different levels. For example, with AI, not all of us today are data scientists, as one of the keynote speakers was saying today. Not all of us are training models. Some of us are just using models to build applications on top of them. And this will be probably the reality with quantum computers as well. Some of us might be more involved in the algorithmic part of quantum computers. Some of us might just be users using quantum computers to our advantage. We don't know, but still, it's important to start experimenting with them today and understanding how they behave today to be prepared for the future. So how can we do this? We can do and start today by using simulators. Now, there are some quantum computers that we can buy. For example, very small, very expensive, but there are some. There are some big companies that make available their quantum computers to us. We have to subscribe, for example, to IBM's platform and pay something, and then we can use their hardware. Or, to start small, we can use simulators. Now, in this presentation, we're going to see two main categories of simulators. The first one is languages that are dedicated to quantum computing. So we can write programs, manipulate qubits using a dedicated syntax that makes it easier. Q# from Microsoft is an example. And then we have libraries developed for existing classical languages that we can use today to learn something about quantum computing. Now, the first two, Qiskit and Cirq, are for Python. The other one, the purple logo over there, is strange. That is for Java. So we can also, as Java developers, start experimenting today without having to leave the JVM for the Python work. Now, to compare them, we need a problem. And our problem for this presentation will be the generation of a random number. Now, this is something that a classical computer cannot do. Right? On classical computers, whenever we ask our language for a random number, what we really get is a pseudo-random number, which means that we have a sequence of numbers generated from a seed, and whenever we ask for a random number, we just get the next number in the sequence. Right? This is not random, because if we know the seed, we know the whole sequence, and we can predict what's going to be picked next. It turns out, though, that at the quantum level, we truly have 50%, for example, chance for the cat of being killed and 50% for it to remain alive. There is true randomness in quantum mechanics, so we can leverage this behavior to generate a truly random number. To simplify the example, we're interested in positive integers that are lower than a maximum value called max that we pick. So the algorithm that we're going to implement today is a combination of classical computing and quantum computing to show also this hybrid type of computation between the two worlds. The first thing we're going to do is to determine how many bits we need to represent our number. For example, if our maximum value is 10, then we'll need 4 bits. Because with 4 bits, we can represent the integers, positive integers, up to 15. Okay, with 3 bits, up to 7, so we need 4 bits. This is the classical part. Easy enough. There is a formula to do that. It's very easy. The second step involves quantum computers. We have to generate a bit string which contains as many bits as needed to represent our maximum value. So, for example, if the maximum value is 10, we'll generate 4 bits. And we generate 4 bits using a quantum algorithm, which is very simple, as you'll see, so achieving truly randomness in the number that we generate. Now, of course, this bit string is also a number base 2, so we convert it into a number base 10, and we compare it to the maximum value. If it's greater, then we repeat the whole process over again. If not, we'll just return our maximum value. Okay, so this is a very simple example, but it already shows an interesting pattern of interaction between classical computing and quantum computing. We have a very big problem generating a random number that is not solvable on classical computers. So we reduce it to something small, generate a single random bit. We solve that with a quantum algorithm. And then on that solution, we build up to obtain a solution of our big problem. We generate many bits to obtain a truly random number that's large, that might be very large. This is known as problem reduction. It's very useful in computer science, mathematics as well, but also in this hybrid quantum classical computation. Okay, so the first simulator we're going to look at, also by looking at some code, is Strange. Now, Strange is a Java library developed for the JVM. It's probably the only one, or at least the main one for the JVM world. And it contains 2 sub-libraries. We have a high-level library, which contains just a few functions with some quantum algorithms implemented that we can just invoke to get a result. This might very well be what we are called to do in the future. We can just have a few quantum algorithms implemented by someone else, and we can just use them to build our applications. Or there is also a low-level library, which gets us to manipulate the single qubits to implement a quantum algorithm. We'll use the low level just to show how manipulating qubits looks like in Strange. Now, Strange's API is very straightforward. As you'll see, if you come from a Java world, if you have a Java background, it's very easy for you to pick how to write quantum programs using Strange. You have a simulator, a sequence of steps. You can just combine them to have a big quantum algorithm. But still, this is not, and so it is very useful for educational purposes. It's actually the first library that I studied for the quantum computing world. And it's very nice. For research, it's still, I think, a bit immature. There are some things that are left out. For example, noise modeling, which makes Strange less suited to trying to optimize quantum algorithms or to prepare quantum algorithms to be run on real-world hardware. But still, for educational purposes, if you don't have any quantum background, Strange is very useful, and it's a very good library. So we'll look at some code. Now, I am mainly a Scala developer, to also show the interoperability of the quantum and classical computing. I wrote a short Scala example. Now, you can see here we have a trait. This trait is an interface if you don't know Scala. It's more or less the same of an interface with a single method to generate a number. Now, I also have a classical implementation which relies on the random class from the Scala standard library. But if you look at the documentation of this method, if it works, looks like it's not working. So the documentation says that the number returned by this method is a pseudo-random number. So it clearly says that there is a generator being initialized, that the generator has a sequence of numbers, and that the next long returns the next number in this sequence. So this is not random at all. The quantum part, on the other hand, is it achieves truly randomness, of course, if we run it on real-world quantum hardware. So the first thing in Strange is to build a simulator. Now, Strange at the moment only have a local simulator, so we cannot run it on the cloud. We cannot send our code to real-world hardware. Still, we can simulate it on our local workstation. Then we have a program, and the program is simply a sequence of steps. Now, a step in Strange, you can imagine it as a moment in time when we have several operations applied to a set of qubits. So it's just a sequence of operations. In our case, the program operates on a single qubit, which is the meaning of this one here, and our step has only one operation, which is this Hadamard operation. Now, the Hadamard operation is the equivalent of triggering the quantum experiment with the cat. It puts the qubit into superposition, thus giving us 50% chance of reading 0 and 50% chance of reading 1. Okay, this is all it takes. Now, the only problem that I have with this instruction over here is that qubits are referred to using indexes. Now, this is fine when you have just a few qubits. If you have complex programs, it might get a bit awkward and difficult to understand and to remember which qubits are identified by which index. Still, this is what we have. And so the quantum bit generation only takes running our program. This will initialize the qubit to state 0, put the qubit in superposition, and then we'll measure it. Now, by measuring it, we have 50% chance, if we run it on a quantum hardware, of course, to get 0 and 50% chance to get 1. Now, another thing that's a bit weird and strange at the moment is that the result of this measure operation is an integer, which is guaranteed by the library to be either 0 or 1. But for example, here in a Scala program, it would be better to have something more strongly typed, right? something more closer to a Boolean. Still, this is just a minor thing. It's just some type level thing. What we have here, we are guaranteed to have either 0 or 1. This is all it takes to write a quantum program that generates a random bit. Okay, the rest of the program is simply Scala code, leveraging a bunch of Scala constructs like a fold, which you can imagine as a for loop in Java, some tail recursive functions, which again you can imagine as while loops in Java that compare the generated number to our maximum value. This is all Scala code. So this shows very clearly how we can integrate quantum algorithms also in a completely different language like Scala. We can use functional constructs like fold, like recursion, to achieve something and to mix it with quantum computing to achieve an hybrid application that we can use in any JVM that we have. So for example, if we run this application, I have it here. If we run it, then it's going to generate, now our maximum value here is 10,000. It's going to print a bunch of logs, one for each time we run our quantum program, and in the end, it will return a bit string. Okay, a bit string, which is a decimal number as well. So in this, is it normal? Do you have like some technician here? No. Okay. Maybe I can try to do this. Okay. Looks like we're good. So I was saying this is generation of a single random number. If we run it multiple times, well, sometimes we'll get numbers that are greater than 10,000, and so our algorithm will repeat the whole process again. Now, this was strange. A completely different approach is the one taken from Qiskit and Cirq that we'll see later on. These are two libraries based on Python. Of course, Python is still in quantum computing kind of the de facto language because it's mainly used for research applications at this time. Qiskit in particular is probably the most comprehensive software stack for quantum computing. It contains many tools for algorithmic optimization, development, also noise simulation. It's very nice for noise simulation because we can actually take some noise models from real-world computers, quantum computers, and then run our algorithms using this noise model. So this actually makes us simulate our algorithms using real-world conditions that then we have when we run on real-world hardware, which IBM lets us do. It provides some quantum computers that we can use to run our code. Still, Qiskit is very difficult to pick. Besides being based on Python, which you may or may not be familiar with, Qiskit has a very, it has a difficult tutorial to follow. It already assumes some knowledge about quantum computing. At least it shows many equations, which is, they might be difficult to understand if you don't know the theory behind them. So it's a bit more difficult than strange, and so it's less advisable for a complete beginner. The same goes for Cirq. Cirq is the same thing of Qiskit, but developed by Google. It's, again, a very advanced simulator. Again, it provides us with many tools to simulate the noise. It allows for, again, deep optimization of our algorithms, and it allows for integration with existing quantum hardware, even if not Google's, I think. But still, again, Cirq is very advanced, very used for research purposes, but still very difficult to pick, again, if you are a complete beginner on the topic. So They are kind of in the two different ends of the spectrum, and this is also why we are not looking at any code for Qiskit and Cirq, because it's a bit more difficult to understand. But by the way, at the end of the presentation, you have a pointer to the code, to a repository where you can find all the implementation of our example in the different libraries. Now, the last one will be Q#. Q# is a completely different approach. So this is a dedicated programming language for quantum applications. Now, if before we kind of took for granted that we could mix classical instructions and quantum instructions, this is not true anymore if we use a dedicated language. But Q# actually provides us with some nice integration, again, with Python. But in the future, it could be also for other languages like Java, for example. So it's built for hybrid classical and quantum computing applications. Again, Q# is hardware agnostic, meaning that it doesn't really forces us to implement interactions between a qubit that are also feasible at a physical level. It takes care of mapping logical qubits to physical qubits, because in general terms, we can have many physical qubits that we need to implement a single logical qubit. And it has, again, configurable noise model. So this is, I would say, in the middle ground between Cirq and Qiskit and Strange, because it's easier to pick. We'll also see some code for it, but not as advanced as Cirq or Qiskit. So the code is, again, the same, but as you can see here, we have dedicated syntax to deal with qubits. So for example, in Strange, we had indexes to refer to qubits. Here we have a use keyword, and we can give a name to our qubit. So this is going to be much simpler. Now, the advantage is not immediately evident here with just a few instructions, but if you have a complicated algorithm, then having the possibility to give a name to the bits is still very useful. So in this case, we apply again the Hadamard gate. As before, this is known as the H gate in Q#, and then we measure the qubit. So this is the same as before. We just apply a single quantum operation that puts the qubit into superposition, and then we measure it with 50% chance of getting 1 and 50% chance of getting 0. Then we reset the qubit. This is needed for some physical constraints, and we return it. So this is all it takes to implement our simple algorithm in Q#, which also has some instructions, as you can see here, to implement for loops or to convert numbers from the base 2 to base 10. So we can write a full application already with Q#, or we can invoke Q# programs from Python code. So if we run this function here, for example, 100 times, then you see we'll get, depending how many times we run it, different percentages of how many times we get 1 and how many times we get 0. So this, if we run, again, this operation on real-world quantum hardware, will give us 1 or 0 with truly 50% chance. And again, we can run the whole program, and as before, you will see a generated sample. And then if you run it many times, of course, there you go, you will generate, for example, numbers that are greater than the max. And then the application will repeat the whole process again. So in this case, again, this is all done with a quantum language, but we could use Python again to invoke our application. So in conclusion, we saw today that even if quantum computing is still many years away, even if it might look complicated, we still have some possibilities to start learning it now. And this has many advantages for Java developers, for example, as we saw with Strange. If it gets more advanced, we can use constructs, syntax, and code that's familiar with us to write applications that leverage quantum computing, even if we don't really know what's going on under the hood at different levels. We can start experimenting now. This is also a call to action to you to start experimenting either locally with the simulators that we saw on the cloud. We have many simulators available on the cloud, IBM's, Google's, AWS's as well, or on real-world quantum hardware. Again, this is available on the cloud, or you can buy a small quantum computer with a few qubits to experiment with it. Even if this seems very farther away in the future, there are some quantum principles that are being leveraged today by many companies. Number generation is one. We also have quantum key distribution, which means we use some quantum principles to exchange secrets between untrusted parties with physically guarantees that we can determine if we are being eavesdropped or if the secret key has been tampered with. So we have quantum applications being used today in many different sectors. We also have a talk on post-quantum security, which will talk about these things, I guess. And many more applications are still possible in the future. Besides cryptography and also material simulation, there are also a lot of different possibilities for healthcare, drug simulation, and so on, which we don't know if they are possible, but we are investigating. Quantum machine learning is also something that's being investigated if you're more into the AI part. So thank you very much. And I hope you enjoyed this presentation. If you have any questions, we're just here for a few minutes.